Okay. You guys, we are going to do something really awesome today. It's called, I got to keep my life spiced up. So we're going to learn about transfer functions via impedance, and then we're going to do an example that I wrote up last night but did not actually solve. So we're going to solve it together, okay? When you first become a professor, they say never, ever do this. So I do it occasionally just for, fun. Okay. Yeah, right? Let's see how this goes. It might be a train wreck. We will see. Like certain American figure skaters last night in the Olympics, might just be a bad night. Huh? Okay. So, now the true power, we've done impedance-based modeling for a couple lectures, right? But the true power of impedance-based modeling is revealed. We can skip a time domain model, for example, state space or input-output differential equation, which are the two types that we've found in the past, and derive a transfer function model directly. In the past, we found transfer function models by transforming an input-output differential equation or a state space model to a transfer function. But these impedance-based modeling techniques allow us to do that directly without having to go through those time domain models, which is actually pretty handy in certain cases. So that's what we're going to learn in this lecture today. Before we do, however, let's be sure to recall that a transfer function model concerns itself with the forced response of a system, ignoring the free response. So it takes an input and it tells you what the output is from that input, right? But if you have initial conditions, it doesn't tell you what happened. So if you are interested in the free response, then you can convert the transfer function model into an input-output differential equation and solve that, including using Laplace domain methods to solve it if you want, which is fine. Remember that when we derive the transfer function, we use the Laplace transform, just like we would to solve a differential equation with Laplace transform techniques. But then we ignored the free response aspect to derive the transfer function. So we could go back up to the differential equation and then we could do it. So it's not like this is useless for free response stuff. We could just back up. So it becomes this thing where there's 15 ways you could do it, and so it's sort of a decision. Could be just stylistic or whatever seems easiest to you. So there are two primary ways impedance-based modeling is used to derive transfer functions. The first and most general is described in this lecture. The second is a shortcut, most useful for relatively simple systems, and it's described in section 5.5. And it's actually a really powerful shortcut, and you can use it on a lot of systems. So I say relatively simple. You could use it on more complicated systems if you wanted. It's just it always comes down to what do you want out of it? How quickly do you want an answer? Is this like a quick back of the envelope sort of calculation that you're doing? Or is it something that you want to do a detailed analysis of and reuse over time? So it kind of depends on what you're going for. But the shortcut method I will highly recommend for I think it really gives you a quick way to get to a model. It's really pretty powerful. But I'm going to teach the general way first, and then we're going to see how nice the simple way is. And actually, to kind of give away the punchline here, it is essentially the voltage divider or the current divider rules. You can use those for general systems, not just for electronic systems. So that's what we're going to do. We're going to use those nice voltage divider sort of concepts to do it. But before we do that, we're going to be more general and say, oh, okay, maybe we don't want to be all fancy and shortcutty. Maybe we want to just do the whole thing. So we'll do the whole thing first, and then we'll learn some shortcuts. So, in what follows, it is important to recognize that in the Laplace domain, every elemental equation is just the across variable. This is the generalized across variable v. The across variable is just equal to the through variable times the impedance of the element. Okay? Which is pretty cool, but remember that's how we derived the impedance of each element, right? We took the Laplace transform of each element and we said, oh, well, the impedance is just v over f, and that's equal to z. So that's why we've already been using this equation to derive the impedance of each element, right? I'm in 517 very explicitly stating that. So now when we think of things in terms of the Laplace domain, every elemental equation is just this with a subscript, right? So like if it's a voltage, it's V, maybe of a capacitor, it's C equals IC ZC, right? So you put in the cross variable or the through variable associated with that element, and the impedance is associated with that element. So they're all the same. So every elemental equation, it's kind of boring to write the elemental equations in the Laplace domain because they're all the same equation, just with different variables in it. So for what that's worth, something to keep in mind. So this algorithm that follows, and it is an algorithm, is very similar to that for state space models from linear graph models. Remember that, presented in volume 1. In the following, we consider a connected graph with B branches, of which S are sources, split between through variable sources, ST, and across variable sources, SA. There are 2B minus S unknown across variables and through variables. So that's how many equations we need. We have B minus S elemental equations, and for the rest, we will write continuity and compatibility equations. N is the number of nodes. So this is our setup, and now we're going to learn the algorithm. So the first step is to derive 2b minus s independent Laplace domain algebraic equations from Laplace domain elemental continuity and compatibility equations. So step 1 is to draw a normal tree from the linear graph. So I'm assuming that you drew the linear graph first. So that is, we could draw the linear graph and then draw the normal tree. Also B, in your notes, I got rid of it. The way that I wrote the algorithm, you don't have to know which variables are the primary and which variables are secondary variables. So it's actually, the way we're drawing this up, it's irrelevant which one is which. I mean, it's kind of interesting to know, but not important for this algorithm. So our new B is to write a Laplace domain elemental equation for each passive element. So V equals Fz, but in whatever form that element is, over and over and over again for every passive element. Okay? And then we write a continuity equation for each passive branch by drawing a contour intersecting that and no other branch. Boy, this is familiar. Same continuity equation as before. And write a compatibility equation for each passive link by temporarily including it in the normal tree and finding the compatibility equation for the resulting loop. So going around the loop and adding up the cross variables. So that's also the same as before. We don't have to solve these for the primary or secondary variables though, because sometimes our outputs that we're going to be solving for might be a secondary variable. So we don't really need to eliminate those. So I'm just ignoring the fact that those are definitions. Okay, and then we're going to solve, so that's the whole setup, and then what we're left with is actually to solve the algebraic equation of 2b, and I have to put in, here's a typo, it's 2b minus s equations and 2b minus s unknowns for outputs in terms of inputs only. So I forgot that B we had defined as being branches in general, including source branches. So we have to subtract out the source branches, essentially. That's the part I forgot. So we have an algebraic system, right? In the Laplace domain, there's no derivatives. So we just have this algebraic system, and we just solve for the outputs in terms of inputs only. If we have one output and one input, then that's usually pretty straightforward to do. But in general, you could solve for any number of outputs in terms of any number of inputs, okay? Sometimes solving for all unknowns via the usual methods is easier than trying to cherry pick the desired outputs. So what you have is a linear system of equations, assuming that it's a linear system, which most of our systems are going to be considered linear. So a linear system of 2b minus s equations and 2b minus s unknowns. And you guys have been subjected to countless courses in which you had to solve that, right? So maybe you did it for sets of 2 equations when you were in a certain grade, and then they did sets of 3 equations later, and you were like, oh my God, are there sets of 4 equations? And there are, when you got to college probably, they were like, use Gaussian elimination, right? Oh man, remember that? Because you wanted to just do substitution always because it seemed easier, and then they're like, yeah, but with 4, you go around in circles forever. So then you start doing elimination. You learn all these things. And then linear algebra, they teach you in general how to solve it using linear algebraic techniques, right? Like inverse of a matrix, all that good stuff, right? So I'm leaving open, use whatever method you want to solve the system. Sometimes if you want just one of them to be solved and eliminate all of the other variables that are not inputs in the equation, you don't have to go through and solve the whole thing. Sometimes though, it's easier to just solve the whole thing than to solve for one thing in there, or maybe 2 things in there, whatever you're interested in. So, and then you've got these solutions that look something like this. So for a given output, say yi, and I'm using capitals because we're in the Laplace domain, right? For a given output, you've got some term multiplying some input, say uj, plus another term multiplying another input, say uk. And in order to find, so step 3 is to take the expression for the output that you're interested in and set all of the inputs equal to 0 that are not the input that you want the transfer function for at this moment. Okay? So say you want the transfer function from uj to yi. Okay? These are just some input uj that you care about and some output yi that you care about. What you do is you set all the other inputs to 0 temporarily. So you say, oh, okay, this is 0. Maybe if there was like a ul is 0, etc. And then you have this expression that you can just divide both sides by uj, and you get yi over uj equals whatever this is. And that is by definition the transfer function from input uj to output yi. No time in there did you have to solve a differential equation. No time in there did you even see a differential equation. you just got yourself a transfer function by skipping that whole time domain stuff. You never saw time at all. Time was never there. So that's like the general method, okay? And let's apply it. First, any questions on the algorithm? Okay, so now is the part of the show where I do an example in front of you guys live. This is gonna be fun. So, fire a hose. Sometimes in this class it feels like, no, that's too easy. We're gonna skip that. So for the schematic of a fire hose connected to a fire truck reservoir, C. So here's the schematic, here's the reservoir C. It's connected, the fire hose is connected to the reservoir with a pump in between. So this pump is going to, of course, increase the pressure by some amount. There's already going to be some pressure head from the tank, right, the reservoir. And we're going to spray water out the end. Look at how artsy that is. Look at that. It's pretty cool. I would buy this and hang it on my wall. Okay, so this is a pretty simple system. Reservoir, pump, and then we've got a hose which we're going to model with an inductance. Well, see, here I go again. Inductance versus an inertance. I do it again. There are so many inside jokes in this class, I don't even know. It's ridiculous. You're supposed to let me know what's going on out there.
We can't see the drawing with the projector.
Oh! Well, hopefully you can see it in your notes. Oh yeah, maybe it'll help.
You know what, Rico? I think Eric's got to be here. That drawing's pretty brilliant.
You still can't see it.
Just nothing.
I can't see it.
But you can just
Well, hopefully you guys all have your printouts and you can see it.
It doesn't really print out too well either, but
Mine works nicely.
Yeah, you got to print in color. See, this is the cyan color mixed with 30% white.
You gotta get rid of that one.
just like
That's
me.
what this color is. I should probably darken it. Oh man, I really should not comment. I really should not.
90% white.
Okay. So we've got this problem here, right? And then I once again wrote L because it's the generalized inductance. Oh, I told you guys also to print another set of notes too, right? Well, it was just from the appendix. It was a table. I'll pull that up as a reference for us. So
I lost it. It's already gone.
it is from C. Appendix C.
Those legs intact red ski competition. Contact.
So this is the table, and let's just take a moment to enjoy it, because you guessed it, I spent a lot of time on it, so I'm gonna make you guys use it. So, this is like, I'm trying to make this a table that's like a go-to for you guys when you're like, oh, okay, I'm working with a fluid system. What is the cross variable in fluid system again? Oh, it's the pressure. What is the through variable in a fluid system again? Oh, it's the volumetric flow rate, Q. What is the A-type energy storage element? Oh, it's a capacitor. It has capacitance C, This is the elemental equation for it, and here's the impedance. The T-type. What?
This would have been nice for mechatronics.
Yeah.
This would have been really
I'm
nice.
gonna include it in the future in mechatronics. I mean, I just made it.
I broke out this like 5 times.
I created this thing this week though, so I didn't have it for mechatronics. But yeah, I was thinking about, because the book does a lot of different tables, but you have to go to a different table for like each thing that you want. Impedance is a table, and the other thing's a table, and I'm like, maybe I could just make one table to rule them all. Because I'm a good nerd, so I have references like that. So this is my attempt at that. So it's got everything in there. Oh man, why do we not have a T-type for thermal? What is that about? It doesn't have a T-type. Crazy. Why did I call the inertance of this fluid system L? Does the table help us? It really should be I, but why did I think it was L? Because it's a generalized inductance. Right? Yeah. Okay. This is the table to rule them all.
Okay, I was just like, are they all?
All there, man. Everyone. All of the types of systems we're going to consider. All the energy domains that we're going to consider in this class. So, yeah. Cool. So that's there.
Is that recoil?
The mom of inertia. Yeah. I had to abbreviate some things. The one table to rule them all needed to be compactified a little bit. Okay. So, because it was at first the one table to rule them all, but it was on 2 pages. Needed to shrink it down. Okay, so we have ourselves a nice problem for those of you who printed your in color.
Or just a really good house fire.
Yeah. So, and I did look it up. I was like, fire trucks carry water, right? Because I know that they have the hydrants, but like they have to carry water too, right? 300 to 500 gallons according to mentalfloss.com. But that's only enough to put out a dumpster fire, apparently.
Really?
Yeah. So anyways, we've been very distracted for the last 8 minutes. So let's continue to do this problem. So what's our first step? Our algorithm's got steps. Well, we'd have to draw the normal tree, but we have to, of course, first draw the linear graph. So let's draw the linear graph. So step 0, draw the linear graph. Linear graph. So fluid system, we have to choose a reference pressure, right? That's got to be our ground. So the reference pressure, let's choose to be the atmospheric pressure. It's typically the reference pressure that we want. Most commonly. Okay. What other distinct pressures do we have in this system? We've got a pressure at the bottom of this tank, right? So there's that pressure. And it's got a capacitor associated with it, so we could draw that to ground. And then that capacitance, so that connects to P atmosphere, right? That makes sense, because open to the atmosphere. It's not a pressurized vessel, it's just a tank. So we've got ourselves the C, and then it's connected to this pump, and this pump is going to increase that pressure, right? It's not going to go back to atmospheric pressure, it's going to increase that. So it's a source, pressure source. And it's going to go into the hose, which got an inertance associated with it and a resistance. And the resistance is going to be, through the hose. It's going to also be the nozzle. But I'm going to include them all into one resistance. Okay. I mean, we could separate them out, but for this model, we're just going to say we're going to lump them all into one resistance. And that connects us back out to atmosphere, right? P atmosphere. So we have to go through. The order is irrelevant, but the key is that they have to be in series, an inductance and a resistance in series, because both elements need to see the same flow rate. Okay? So that's kind of key. So we can do either order. I'm going to choose L and then R, but we could have chosen them the other way. It would have been fine. So we just have this big loop, and that's our linear graph, right?
It's the electrical system.
What did I do with that? Okay. So that's our linear graph. What's our step 1?
Normal tree.
Yeah, 1A, normal tree. So I'll use another color and just superimpose. Actually, no, I'm gonna just select those branches and change the color. So A-type energy storage elements and cross-variable sources are high priority. The next priority is resistance, or D-types, right? And the lowest priority is the inductance. So I'm going to just change these colors to some really obvious colors you guys can see, which I'm choosing green. Can you guys see that? Yeah. Okay. So, and then of course all of the nodes are selected. We typically get lazy and we don't explicitly colorize them, but I'm going to colorize the ground node at least, just to make it clear that that's part of it. This is only one node though, right? This point and this point are connected. So we can't select the inductance L, aka the inertance L, slash I, because we would create a loop, right? We can't do that in our normal tree. And we can't select anything else, so we're done. Done with our normal tree. Now, A, B. Yes, I was just reminding myself of the order of the letters in the alphabet. B, Laplace domain elemental equation for each passive element. Okay, so we can write ourselves a nice little table here. We have 3 elements, so C, I, and R. And let's write the elemental equation for each. So they're all going to be the cross variable equals through variable times the impedance, right? So the across variable in a fluid system is pressure. So PC, and these are all in the Laplace domain, and I'm not going to write of S 50 times. I'm instead just going to suppress that. But we know these are all in the Laplace domain. So PC equals, the through variable is Q, right? QC, the flow rate. QC. And then times the impedance, ZC. Then for our inertance, PC, or PL, PI, something, PI equals QI. And then what is it? It's Z what? ZI. Or maybe ZL. Who knows? Bingo. Sadly, every time I hear bingo, now I think Muckleshoot Casino. Machine Go. You guys heard that? That's horrible. Thank you, America. Okay. PR is equal to QR times ZR. I think they have radio commercials or something. I don't know. Who knows? I didn't even know. Just like appears in my head. You guys are lucky. It might seem like I don't filter stuff that comes into my head, but I do. Okay. So this is our CI and R elemental equations. Elemental. It's pretty easy, right? And the same equations 3 times. Now we've got C continuity, D, compatibility. So we just got those next. So let's go on to the next page and do C, continuity. And we need to do a continuity equation for each of the elements that are in the normal tree, each of the passive elements in the normal tree, right? So we need to know, we need to draw these contours. I mean, to go through the whole process. Let's not take shortcuts on this one. We need to write a contour for each passive element in the normal tree, which is to say we need to write a continuity equation for C and one for R. We do that by drawing a contour that intersects the normal tree just through that element and nowhere else. So in order to do that for C, we kind of have to do this contour, right? We could draw it around this way, same equation. And for R, it's a little easier. We can just do that one. So our C continuity equation is just going to say that QC is equal to QI, right? Oh, am I wrong? Is there a sign there? Let's see. So they're both leaving the contour, so they have to have opposite sign, right? So QC equals negative QI or negative QC equals QI, same thing. And then R, we have just essentially a node to look at, and we see that QR is equal to QI, right? So I have to confess, last night as I lay in bed I couldn't sleep, so I decided to work this out in my head before, and I missed the minus sign in my head last night. So this is why you should never trust yourself when you're laying in bed at night trying to figure out a problem. You're going to drop a minus sign. So we're now in uncharted territory after having dropped that minus sign. So we have a single.
Really is interesting.
It's weird. It's weird. I mean, I have a good time most of the time. Yeah, so I needs to be inserted into the normal tree for just a moment to write a compatibility equation around this loop, right? So PI is going to equal, we're going to go around the other way. So negative PS plus PC minus PR, okay? So this is for I. So we're going to say PI. I regret putting the top and bottom on the I. It's a lot of extra strokes there. PI equals negative PS plus PC minus PR. Negative PS plus PC minus PR. Okay, so those are our continuity and compatibility equations. So now we have, we've reached the end of 1, right? Now we're on 2. Solve this algebraic system of 2b minus s equations and 2b minus s unknowns. We have 6 equations and 6 unknowns, okay? So 2. Solve. Now, what we care about is the nozzle velocity, right? The velocity of this spray coming out of the nozzle. And I gave you the cross-sectional area, so what do we want to solve for to decide what the velocity of this fluid is going to be coming out the nozzle? QR, which actually there's only one flow rate going through the whole thing, right? It's going to have different cross-sectional areas, but our continuity equations are telling us that within a minus sign, we have one loop here. So the flow rate's got to be the same for all of these elements. So we want to find flow rate, QI, QR, QC even. Any of those would get us to our result. So we could set up a set of 6 equations of 6 unknowns and solve for all of them. So our 6 unknowns are going to be PC, QC, PI, QI, PR, QR, right? Solve for all of them. But frankly, we don't need to for this problem. So let's see if we could solve for one of these Q's without having to go through a whole lot of work. So I'm looking at these. So we've got all the Q's here related to all the P's, right? So I look down here and I say, we're going to have to bring in this equation because we know we're going to have this source, PS, show up in the answer, right? We've got to eliminate everything besides the input. So the input's got to show up in there. So we got to get that in there. Our QI equation would get us started towards this solution pretty rapidly, right? So let's try that. Let's plug in to our PI equation. So our PI equation says that QI is equal to 1 over ZI times PI, right? But we're going to plug in this compatibility equation instead. So negative PS plus PC minus PR. So we need to eliminate from this PC and PR. So we're probably going to need to use these compatibility equation, or these elemental equations. So PC is just equal to QC ZC, right? So let's do that. 1 over ZI negative PS plus, instead of PC, we're going to say QC ZC. And instead of PR, we're going to say or QR ZR. And we have continuity equations that tell us what QR and QC are in terms of QI, which is on the other side of the equation, but is what we're solving for. So let's try that. So equals 1 over ZI times times quantity negative PS. QC is negative QI, so minus QI ZC. And then QR is just QI, so minus QI ZR. Okay. Now we need to bring these QI terms to the left-hand side and factor out QI, divide back through by everything else, right? That good old move where we move over, factor out, divide back over. I swear I could do this one while I'm already sleeping. All right, not just laying in bed awake. So QI is still going to be on this side. And let's kind of do the adding over, the factoring out, and the moving back over all in one step because we like doing that. I like doing that. It's fun. So there's this negative sign still from the negative PS. So negative 1 over ZI is still left over here. And then we're going to divide by, we added these over. Important to remember that when they came over this way, they picked up a ZI. Maybe it would be better to think of having moved the ZI over, brought these guys over, and then factored out QI. I think that's a little easier. So then we're left with just negative 1 here. Actually, Yeah, there's a PS, right? So -1. We'll put the PS out here. That's our source, right? We're thinking transfer function already here. We're starting to get our hopes up that we've got it solved, right? We're feeling good about it. So we're saying, PS is out there. So we're left with a -1 PS. The other side had a QIZI, a QIZC, and a QIZR over there. So when we factored out the QI, we had a ZC, or I think it probably makes sense to draw the ZI first. ZI plus ZC plus ZR. Okay? And yeah. Did I do something wrong here, or am I good?
You actually did it right. No, you
I think that's right. That's
did it
right.
right.
Okay.
Despite our expectations.
Yeah. Oh. So here's a conundrum. You know how they say that it's rude to salt something before you try it? You're supposed to try it. It's good manners to try it first and then salt. But, and the idea is that you don't trust the person. You're just going to salt it and you're like, oh, this is going to suck, right? And you salt it first. However, aren't you just saying this particular thing sucks when you taste it and then you're like, ugh, salt. If you start out and you say, I salt everything, you know, it's not you, it's me. I salt everything. You have that out. I'm just saying maybe we're wrong about what's rude. So QI is equal to negative.
Respectful, I just think it's smart because it might be salty that you put salt on it.
It's definitely rude if you're like, this sucks, I need to put salt on it. That's definitely rude. I'm confident we can all agree. So this is very close to our transfer function. What is left? So step 3 is to set all of the y's, or all of the u's equal to 0 that are not the u that we care about. There's only one u in this problem. There's only one input, right? It's PS. So setting all the others equal to 0 is pretty easy. It is already done. So we don't have to do that. So all we need to do is divide both sides by our input. So step 3 is to divide both sides by PS, and we get QI over PS, which is equal to -1 over ZI plus ZC plus ZR. Yeah. So, pretty good times. I think it's pretty fun. I think we did it right too. I mean, I don't know. I don't always trust myself when I do stuff in front of a class because it can get a little nervous, you know. But I'm pretty sure we got that right. And notice we got this transfer function relatively easily. I mean, we kind of BS'd a lot. But not too bad. Any questions on what we did or why we did it?
Why is it negative?
Oh, why is it negative? Let's see if we can figure out why that is. Oh, but we haven't even found the velocity yet. We're not even done. Thank God we have another minute, right? It's because we have to find what the transfer function is between the velocity. Okay, so we can just call it v. It's the only velocity we care about. V divided by QI, right? So what does that equal to? It's 1 over the area, right? It's 1 over the area. This is going to take us from meters cubed per second in SI to meters per second. So we need to multiply our result by this, which is to say, we say QI over PS times V over QI gives us what we want. So QI's cancel, and we get V over PS, our transfer function from the pressure of the pump, which conceivably we could adjust, right? Adjust the pressure of the pump. We get a different velocity out. So we just need to multiply 1 over A and this, and it's just negative 1 over A times, or divided by ZI plus ZC plus ZR. Now, we should probably plug in what ZI, ZC, and ZR are, right? There's S's in there and stuff from the ZI and the ZC. Second order system, you know, we should probably simplify that. But we've got what we're looking for, the transfer function. The negative sign is going to come down to the direction that it's going.
Pressure drop should have been the other way. The source, because you have a source.
So yeah, so we drew our pressure source opposite of what it actually would go, right? Because it's going to drop from this to this, because it's going to be a pressure increase.
Yeah.
So we should have probably drawn our pressure source the other way. But the negative sign at least alerted us to that fact. So. All right, good times.